In this demonstration, we're going to look at crystal symmetry. The symmetry of a crystal reflects its internal atomic structure. It might seem quite surprising that in this box, I've got lots of crystals of the same mineral. Quartz, quartz, more quartz, and even more quartz. These crystals kind of look a bit different, but at the same time, they look similar. Let's take two of them. This one is bigger than this one. But there's a similarity between them as well. And that similarity we describe by the angles between the crystal faces. Let me show you what I mean. This is a gonometer. It's designed for measuring the angle between crystal faces. So if I take this gonometer and place it here, I can measure the angle between the two adjoining crystal faces. I need to turn it round so I can see it myself, and it appears to be 120 degrees. I'm going to rotate the crystal now, and look, it's exactly the same. And again, exactly the same. Indeed, all 6 of the faces of quartz, the angles between them are always 120 degrees. And if I take a different quartz crystal, I haven't changed the gonometer, exactly the same. And I'll go on, I'll take the small one as well, just in case you're not convinced. There we go. The shape of the crystal is indeed determined by the arrangements of the atoms within that crystal. We refer to the arrangement as the crystal lattice. Let me take an example of that. This beautiful rhomb-shaped crystal is calcite. It's quite different than quartz. And take another one. Again, you can hopefully see the similarities in shapes. One is bigger than the other, but the angles between the crystal faces are the same. Here's a long one. The angles between the crystal faces are still the same. So why is that? It is the internal arrangement of the atoms. And here I've got a model of the same crystal. This is the arrangement of the atoms inside a calcite crystal. Let me introduce you first to the atoms. Calcium is the silver ones. Carbon is the black one, with 1, 2, 3 oxygens. That's a carbonate ion, a calcium ion. Combined, it makes calcium carbonate, which is calcite. Now, look at the shapes. Can you see that they actually have the same rhomb-like shape? The shape of this crystal is determined by the arrangement of atoms inside it. I'll put that there. Okay. We can use this to allow us to think about the symmetry of a crystal as a diagnostic. I'm going to now take a few examples of the types of symmetry we can refer to. Maybe it's most pedagogic to start with calcite, given that's the one we were talking about. I've got now a paper model of a calcite crystal. Perhaps you can see the same rhomb-like form. So what is the symmetry of the crystal? Well, the fun thing is the symmetry is not so intuitive. We would actually say that calcite is a trigonal crystal. What does that mean? It means it has one threefold rotational axis. That's a bit of a mouthful, isn't it? So let's have a look at it and see what I mean. If you look straight down at the point in the middle, and I now rotate this crystal 120 degrees, it looks the same. And if I do it again, it looks the same. And if I do it one more time, it still looks the same. That's what I mean by a threefold rotational axis. That is the defining property of a mineral that belongs to the trigonal system. I'll do that one more time. 1, 2, and 3. And I'm back where I started. That's one example of a trigonal shape. Let's take an easy trigonal shape now. You wouldn't have been so surprised if I showed you this one first and said it was trigonal. Well, you see it's kind of like a triangle, isn't it? So if I rotate it 120 degrees, looks the same. One more time. And one more time. And I'm back where I started. So this one is genuinely hexagonal. You see, there's a difference now. If I now only need to rotate 60 degrees for it to look the same again. 1, 2, 3, 4, 5, and 6. I'm back where I started. I'll do that one more time. 1, 2, 3, 4, 5, and 6. So that's the hexagonal crystal system. It's defined by one six-fold rotational axis. Okay, let's up the symmetry a bit more. And we're now going to look at the tetragonal system. And here I've got an example from the tetragonal system. It's defined by having one fourfold rotational axis. I think you can probably see it straight away. 1, 2, 3, back where I started. One fourfold rotational axis. 1, 2, 3, and 4. That's the tetragonal system. So let me up the symmetry even more. And I'm going to take this guy here. Well, you'd look at that and think, well, it's also got a fourfold rotational axis, just like the tetragonal system. 1, 2, 3, 4. But it's got more symmetry. This is the cubic system. And it's kind of easy to see this because it's a cube. But it's got nothing to do with the fourfold axes that define it as cubic. Instead, it's the threefold ones. And there are 4 of them. So I'm holding this crystal up now. I'll try and hold it from here, so my hands are not too much blocking it. I can rotate it 1, 2, and 3, and I'm back where I started. That is a threefold rotational axis. That was that point. But what if I took this point here? 1, 2, 3, back where I started. Indeed, a cubic mineral has 4 threefold rotational axes. And if we look at, there's one coming out here, one here, diagonally, one there, and one there. That's actually what defines cubic. It's got nothing to do with the square ends. And I can illustrate that better if we take another member of the cubic system that you might not have thought was cubic at all. This is also cubic. And you're looking at that and saying, well, wait a minute, it's a triangle. How can it be cubic? Well, look down at that point. 1, 2, 3, back where we started. That was that point, but I could take any of the points. I could take this one. 1, 2, 3, back where I started. And I could take the other two as well. It has 4 threefold rotational axes. That's what defines the cubic system. Here's an even more complicated looking one. Look at this guy. That's a nice one, isn't it? I kind of like this one. So if you look at that, straight down at the point, 1, 2, 3. Now that was for that point, but I could equally well have used that point. In fact, I could use all 4 of the points of that crystal. It has 4 threefold rotational axes. So we've taken ourselves up in symmetry from trigonal, we've looked at hexagonal, we've looked at tetragonal, and we looked at cubic. We can also go down in symmetry, and this is where it gets a little bit trickier. I'm going to take you now to the orthorhombic system. And orthorhombic system is a little bit trickier. This is kind of an old model. There's a hole in it there. It's a bit of a shame, but it's a beautiful model anyhow. Now this is defined by having twofold rotational axes. So if you look there, how would I get it to look the same? If I rotated it, if I thought of it as tetragonal, I'd rotate it 90 degrees. It doesn't look the same at all. I have to actually rotate it a full 180 degrees for it to look the same. That's a twofold rotational axis. I could do it that. I could do the same here. Once, and we're back where we started. And I can even do it, which side was on before? I don't remember. We'll do it both ways to be on the safe side. 1 and 2, or 1 and 2. This orthorhombic crystal has 3 twofold rotational axes. We can also sometimes think of these as mirror planes. And a mirror plane is a slightly tricky concept, but imagine if I was to place a mirror right in here. Can you see that to the left and to the right, it kind of looks like a mirror image? That's what we mean by a mirror plane. So I could have defined it with mirror planes rather than rotational axes. That will not always work, but sometimes it will. Okay. Right. What do we have left then? Well, another one we can have, which is very little symmetry, is a monoclinic crystal. It will have 1 twofold rotational axis and 1 mirror plane. You're looking at the twofold rotational axis now. If I rotate that 180 degrees, it looks the same, and it looks the same again. And that's actually the only twofold axis this model has. But it's got a mirror plane. Imagine a line dividing what you're looking at right down the middle. It's like that. It's a mirror image on one side to the other. This has 1 mirror plane and 1 twofold rotational axis. That's referred to as a monoclinic crystal. The last of all is the triclinic system. And you look at this thing and think there's no symmetry at all. But it actually does have symmetry. It's got what's called a center of symmetry. That means I could, if you imagine I went from one end of the crystal to the other end, passing through the middle, and kind of almost like turn the crystal inside out, it would appear the same. So I would go from here through to here. This is a center of symmetry. Oh no, I left one out. That's good. Gives you a chance to think what this one might be. What do you think this one would be? Did you guess hexagonal? If you did, that was right. So we use crystal symmetry to help us identify different minerals. We have the following crystal systems. We have, from the least symmetry, triclinic, just a center of symmetry. Monoclinic, one rotational axis, twofold and a mirror plane. Orthorhombic can be three twofold rotational axes. Trigonal has a threefold rotational axis. Hexagonal has a sixfold rotational axis. Tetragonal has one fourfold rotational axis. And cubic has four threefold rotational axes. And I thought I'd just conclude this demonstration by showing you three different cubic minerals, which might surprise you. Okay, this is a very small one. It's got 8 sides. It has 4 threefold rotational axes. It's cubic. Magnetite. This one, it's got 12 sides, but it also has 4 threefold rotational axes. It's also cubic. You look down at the point, you can just about make out there is a threefold rotational axis. In fact, there's 4 of them. This pyrite is also cubic. And this one, garnet, with 20 sides. It also has 4 threefold rotational axes. Garnet, too, is cubic. Thank you for listening.